What's the output of the X-ray tube in our XRF spectroscopy system? This is a question that makes sense because one of the options that we have in our system when we set up it is to choose the filters that we put on the X-ray tube. So let's have at least a rough idea what's the shape of this output of an X-ray tube. There are few terms that we need to understand in order to describe the output of an X-ray tube. These are the main, let's say. So first of all, we have bremsstrahlung. This is the main source, the main effect that is generating the X-rays. Then we will understand what are the target's peaks, then the tube's peaks and the famous Compton peaks. Okay, so we can start first of all to have a look at an X-ray tube. So there it is. This one on the bottom is the X-ray tube that we have in our system. So it's that class of miniaturized X-ray tubes. There are different types, but they are pretty small, like this one, or even smaller. So basically what we have is over here we have a kind of a resistance where there is a current, and this is important. It's one of the parameters that we are going to change, control in our tube, in our software for the tube. So we have a current here in this black wire, and then basically here there is like a resistance. So when there is a current, this resistance will have a high temperature. And so this high temperature, so it starts to be incandescent and it starts to send off some electrons. So these electrons are over here. On the other side, over here we have an anode. So this anode means that there is a positive potential. So the electrons that are charged negatively, they are attracted toward the anode and they will accelerate. So there is a vacuum, of course, inside this, let's say, this chamber, so there will be glass all around it. So it's closed, there is vacuum, there are here the electrons. The electrons are attracted toward the anode. Then over here there is a material that when we purchase the X-ray tube, we can choose. There are different kinds, so could be copper, could be silver, could be gold. Our system is made of rhodium, RH, rhodium. On top of the anode there is this piece of rhodium. The electrons strike into the rhodium target and they start to have some interaction between these electrons and this material, the rhodium. So let's do now the experiment. So we move in the lab and we do acquire a spectrum of the tube without any filters on it. So over here, this one will be the window, so from where the X-ray will come off from the system. And we see the system without any filter, so we start to see what we get. Let's move in the lab. So now this is our tube. From here is this one, we can rotate it and we can remove this part. So this one will be the piece where there is a collimator inside, so to have a precise spot, and then over here there are the filters. So now I just use this tape so to show you how it is done. So what we can do now is we want to take a spectrum of the tube without any filter at all. So just the tube and anything else that we can add over here. So this one is just the exit of the tube and nothing that we can control or to add something, just the tube. Let's see what happens. This is the spectrum we acquired from the tube. So the spectrometer is on, we acquire a spectrum, and under the tube there is the HDPE material, plastic, that reflects the X-rays from the tube directly into the spectrometer. We get the spectrum. So you see, this spectrum has different features. This spectrum as it is, so this output from the tube as it is, cannot be used to do the analysis because we have all these peaks over here and also over here, and these peaks will cover the peaks of the characteristic peaks of the material when we do the actual examination. In order to have to do the examination, we need to have an XRF output spectrum that is basically flat, so some curve, but doesn't have to show all these peaks. So let's understand from where these peaks comes from, and then we can start to think how to remove them using the filters. Okay, so basically all these, the bottom area over here, on top of which we have these peaks, this one is called Bremsstrahlung. There it is. So all this ground, this comes from the Bremsstrahlung effect. So what we have, so I made it a little bit of graphics. So remember how the tube is made. So the tube, we have this cathode with the current where the electrons are produced, and the electrons are accelerated toward the anode, that is positive. So and this is basically is where we select the keV, the kilovolts for the tube with the acceleration. When there is this acceleration of the electrons, we have this phenomenon. So this one is the electron. So I made this symbol to indicate an acceleration. So this movement of the fall of the electron. So when the electrons are very close to the target, they start to interact now directly with the nuclei of the target. These electrons, they are decelerated. So in this interaction of the electrons with the electromagnetic field of the nuclei, this deceleration create the emission of a continuous spectrum of X-ray. So the Bremsstrahlung radiation that we saw in the spectrum, that we see in any tube output spectrum. So these are the X-ray emitted from the tube by Bremsstrahlung effect, and they cover a broad spectrum. So this is the main source, the good, actually, these will be the good X-rays that we need for the measurement. Another kind of peaks that we have in our spectrum are these two over here, 1 and 2. These specific peaks are the target peaks. So in this case we use rhodium. So these one are the peaks characteristics, X-rays of rhodium, and are emitted because, of course, when we have these electrons, we also have XRF fluorescence emission directly for the target. And so we have these specific peaks over here. Now we look at another group of peaks, the so-called tubes peaks. So this area over here, you see there are all these peaks, very defined characteristics. These are coming from elements like iron, copper, nickel. And basically these ones are due at the interactions of the electron and the X-ray produced into the tube with the elements composing the tube. So because the tube is, other than have the target, is also made of some electronics. So we have copper wires, we have iron, nickel to make the structure of the support of the target itself, and so on. So those elements that are necessary to make the tube will be hit by the electrons, hit by the photons, the X-rays produced inside the tube, and also they will emit characteristics X-rays. So we have all this series of characteristics X-rays that we have to remove to have a good output for the tube. The last couple of big peaks are this one in green, the Compton peaks. So this one smaller and this one bigger one. So this is a diagram of this Compton scattering. So what happens is that again we have the electron from the cathode, they strike the rhodium target, and X-rays, all those X-rays are produced. In particular, we saw the characteristics X-ray of rhodium as are produced, those two big peaks, the target peaks. Those target peaks, so those X-rays, will interact with the other atoms in the target. So this Compton effect is when these X-rays, so these are the X-ray, they will hit the outer or loose electrons of the target, and in this case there is this kind of inelastic scattering where basically the photons release a bit of their energy to this loose electron that actually can be scattered, so will receive some kinetic energy, and the X-rays will proceed, let's say, their path, but they lose some energy. So we'll have X-rays now with less energy, and those were the actually Compton peaks, the greens over here. Now we understand how a XRF output spectrum is made, what are the components of this spectrum. Now we want to do another experiment. So this is the collimator with the filters that I usually apply on this tube to do my routine XRF analysis. I'm removing the filter. So you see this is the tape that holding them is just put on place. So there are two filters. This one is a aluminum filter, so we put over here, and then there is inside over here below a tungsten filter. So we remove also this one. You see, there it is. It's much thinner. Okay, so what we do now is first we do an examination of the tube with only the aluminum. So we put the aluminum over here. See, this is our filter. We use the tape to bring it in this vertical position, and we screw it back inside the tube. So just aluminum. So this one is the high density PE, polyethylene filter, plastic. So this one acts as a mirror for the X-ray. So basically the idea is that the X-ray coming from the tube are reflected back into this spectrometer. So basically we can see the output of the tube. And we are ready to measure the spectrum of the tube with just the 1 millimeter aluminum filter. This one on top is the spectrum of the tube without any filter. This one is the spectrum of the tube with the aluminum filter. So the aluminum, that is a light element, can stop all the low energy peaks until here basically. So this area is fine from the tube because it doesn't have characteristics X-rays, so can be used. So I can work if I'm just interested to analyze an object that has peaks, X-ray peaks just in this area. On the other hand, this area here it's not suited for XRF examination because we have still the Compton peaks over here and the peaks from the target that are still present over here. Let's see now what happens when instead of the aluminum filter we use the tungsten filter, just that one. So we remove this filters holder. It's over here. So this is the aluminum filter. So we remove it and we use the tungsten filter. There it is, and we put in front of the tube. Okay, there it is, it's in position, and we screw it back. Okay, we remove the cover, we put back the reflector, the mirror for the X-ray, and we are ready to do also this measurement. The red one now is the spectrum of just the tungsten filter on the tube. So what we see is that tungsten, that is a very heavy element, can stop pretty well the Compton peaks and the target peaks. On the other hand, tungsten is creating its own peaks. Okay, so these are the XRF characteristic peaks of tungsten. So we will see the ideal condition is when we use first the tungsten filter to stop the Compton over here, and then on top of it we put the aluminum. So the aluminum will stop the peaks of the tungsten. So eventually we are going to have a flat source of peaks of X-rays just in the farthest part of the spectrum. Now we can do the final measurement using both the filter as I do normally. So we put this one to prevent damage to the spectrometer. We unscrew this one. Okay, there it is. So the tungsten filter goes all the way inside. So it's the first filter we apply, the tungsten. There it is. And then we apply the aluminum. There it is. Then we cover with the tape, so they are in place, and then we screw it back. Okay, remove this one, the cover. You can have this one, and we add the reflector. Let's measure it. There it is. This is the red one is the spectrum from the tube with both the filter. First the tungsten over here, and then on top external the aluminum. So we see we get a much flatter spectrum. Of course the intensity of this area is much less, but it's still enough, of course, but definitely much less than what we had originally. We can magnify the spectrum, so we see that this area is totally flat, and then over here we have the actual source of X-rays in the further part to excite the other elements, and we saw that it is practically flat. There is just a tiny bit of Compton over here. So this is the typical spectrum of the output that we are going to use to do our examination.